Welcome to the lecture on fundamentals of MIMO wireless communication. Currently, we are discussing small scale propagation model. After discussing multipath interference followed by flat fading, we are now going to discuss the envelope distribution for small scale fading. The received signal that we have seen till now is represented as real part of sum over C n e to the power of j phi n of t times s tilde t minus tau n e to the power of j 2 pi f c t, and we have identified this part as r tilde t. Now, in order to study flat fading, what we have seen, flat fading is one where in the entire range of frequency the gain is constant, although the gain changes with time with the same gain remaining across the entire frequency. Now, since the gain is flat across the frequency range of interest, we can study it by sending a single tone in that in the whole band of frequencies. That means, if we would use cos 2 pi f c t, or in other words we set s tilde t is equal to 1. So, if we set s tilde t equals to 1, what we will get is the s of t is real part of e to the power of j 2 pi f c t, which is cos 2 pi f c t, or a continuous wave transmission. So, if we are sending a continuous wave transmission, whatever happens to the signal envelope over here, we will expect it to be the same across this entire band of frequencies, because we are encountering a flat fading channel. Now, if we have this, we basically have r tilde t is equal to sum over C n e to the power of j phi n of t s tilde t minus tau n, n is equal to 1 to n or in other words, what we have s tilde t equals to 1. So, we will be having sum over C n e to the power of j phi n of t, and which is also equal to h of t, as we have seen in the previous lecture. So, if we look at this part, we could write this as sum over C n cos phi n of t plus j sum over C n psi sine of phi n of t, and this is, instead of writing as r tilde, because we have taken s tilde is equal to 1, we can write this as h of t. So, what we have as the channel impulse response, which is basically an impulse in our case, instead of a train of impulses which gave rise to this flat fading, as sum of sinusoids weighed by some coefficient C n in the both real and imaginary part. Now, in order to study this, we will take a look at these individual real part and the imaginary part. So, let us say h of t is equal to h I of t plus j h q of t, where h I of t is this expression and h q of t is this particular expression. So, where h I of t is equal to sum of C n cos phi n of t, and h q of t is equal to sum of C n phi n of t. If we look at these expressions, these C n's are basically contributions from the different surfaces on which the impinging waves hit upon, get reflected, diffracted, scattered, or any other process. and there is also this phase component. What we have seen for the phase component is that this phi n of t has a component amongst others f c times tau n, and we have seen that even a small change in tau n gives rise to a large change in phi n. So, with this, that means we have seen in the order of 1 nanosecond if there is change in tau n, this changes almost by 2 pi. So, because of this, it is reasonable to assume that phi is uniformly distributed in the range of 0 to 2 pi. So, this is again an assumption, and this has also been validated. So, this is a reasonably good assumption. So, this is one of the important things we take. Regarding CNs that we encounter in this expression, these as we have seen, it is from the propagation environment. So, there is no fixed number for Cn. These numbers would also be random, and using this method one could generate these channel coefficients directly by the first principle, although there are many different ways of doing it. So, this itself captures a way of generating these coefficients h I and h q together, which gives us h, which can be used in evaluating performance of communication systems. Now, if we will take a closer look into this, what we have is phi n's are uniformly distributed between 0 to 2 pi, and Cn's are random, and one simple assumption on Cm could be that Cn's are all 1. That is also possible. With that, what we have is a large number of additions 1 to n. If n is significantly large, one rule of thumb is n be at least 6, or if it is rather more than 6, we can invoke the central limit theorem for this and for this both. And with that, we can assume that h I of t and h q of t, if we take these values, then they can be assumed to be Gaussian distributed. So, what we have found is through our realization, that means through our model, when we studied flat fading, if we take a continuous wave transmission through which we wanted to study the signal behavior across this whole band of frequencies, what we could get at the end is this channel coefficient, or the received signal corresponding to a tone transmission, or the envelope or the complex envelope of the signal has a real part and an imaginary part. The real part and the imaginary part are made of sum of a large number of variables, and we have made the assumption that phi n is uniformly distributed in the range of 0 to 2 pi. So, therefore, this is a uniform random distribution, and cos would be distributed, cos of phi n accordingly would be distributed in the range of +1 to -1. Same with sine, and along with which there is another random component in the amplitude, which is because of the surface on which the impinging wave hits upon and then arrives at the receiver. So, even if we make the very simplistic assumptions of C n to be 1, we would still end up in a situation where h I and h q, using the central limit theorem, we could say that they could be Gaussian distributed, and we could write down the probability density function of h I or h q as 1 by root 2 pi b e to the power of minus x squared by 2 b, where b is equal to omega p by 2, where omega p is the total received signal power. So, with this going back here, so what we have as h t, which is again I repeat the received signal when s tilde t equals to 1, as can be seen from this expression, or which represents the channel coefficients for a flat fading condition, is basically complex Gaussian random distributed. It is basically complex Gaussian. So, what we see is that h, which is the channel coefficient, is randomly distributed. Now, this is one of the important things which we have said in the beginning, that we want to understand the channel, because understanding the channel will help us in designing transmitted sequences as well as devising the receiver structure. So, one important thing that we come across at this point is these channel coefficients are random. So, if you look at the flat fading condition here, we have values which appear random. It is complex, so it has a real part and an imaginary part, and it is the distribution is complex Gaussian. So, if we take a typical digital communication system where let us say x is the symbol that is getting transmitted, it is a flat fading channel. So, there is multiplication with h, and let us say there is noise which is getting added, and finally, we are getting the received signal y. If there was no channel, or if this was ideal condition, that means if h was equal to 1, that means under ideal condition h is equal to 1. In that case, the received signal would be y equals to x plus w, where w is the noise component, and what we have is additive noise because of the plus, and if we take this as Gaussian and white, we have additive white Gaussian noise. If noise is not present, we receive the perfect signal. If there is noise, we get distorted signal because of noise. So, in that case, suppose we had sent a signal which is like this, what we would receive is, because of noise addition. But now, what has happened is there is h getting multiplied. So, suppose h takes a value, even if we take the real part of it, something gets multiplied, and that multiplication would lead to the level being shifted to any point. If it is opposite in sign, it could go below 0 in this case, or it could go above 0. So, the received signal could be anywhere. It could have been here, and in this case the received signal could have been here. On top of it, we do not know the exact level, and the scaling factor can be different for different symbols. So, the job of the receiver design and the transmitter design would be such that when this is the signal level, those are transmitted, whereas this or this is what is received. We have to reconstruct this signal back. We need to understand the behavior of this. From the current discussion, what we could get is that these h coefficients are Gaussian distributed. So, that means these amplitudes could go to any level, although with different probability values, and accordingly we have to start working on the receiver design. So, based on this, we could write the received signal as the real part of h of t e to the power of j 2 pi f c t, and which is equal to h I of t cos 2 pi f c t minus h q of t sin 2 pi f c t, and once again when s tilde t is equal to 1, the received signal would be that corresponding to a continuous wave transmission. So, this would be the passband channel coefficient, which can be expressed in terms of the band pass in terms of the baseband or the complex envelope of the channel coefficients translated to the appropriate carrier frequency. With these, we also make the assumption that, or we do this put the symbol that omega p is defined as the total received power, that is expected value of h I squared plus expected value of h q squared of t, which is equal to sum over n equals to 1 to n C n squared. And expected value of r squared of t, which is the passband signal, would be omega p by 2, because this is the power in the passband. Now, once we have seen that h I and h q are Gaussian distributed and h is complex Gaussian distributed, what we are interested in as is the title of today's lecture, is the envelope of h of t, which we define alpha t is equal to mod of h of t. So, h t is complex Gaussian, h I of t plus j h q of t. So, this is Rayleigh distributed provided expected value of h I and expected value of h q goes to 0. Now, if this is random and this is uniformly distributed between 0 and 2 pi and C n is independent of phi n, we can easily get that expected value of h I is equal to 0 and expected value of h q is 0. And in that case, we would have E of h I of t is equal to E of h q of t is equal to 0, and the envelope of h t, which is defined as alpha t, that is mod of h t, would be Rayleigh distributed, and the Rayleigh distribution would be given by p alpha of x is equal to x by p 0 e to the power of minus x squared by 2 b 0 for x greater than or equal to 0, where b 0 is equal to omega p by 2, and it is equal to 0 for x less than 0, because alpha is mod of h t and the lowest value that alpha can get is 0. Anything below 0, it is not defined, and hence the probability density function is 0. The interest in alpha t, which is mod of h t, lies because mod of h t gives us an indication of the signal power. So, that is why this is a very important quantity, and this Rayleigh distribution is also one of the most important distribution that you would encounter in the study of wireless communications. Of course, there are many other distributions, but this is one of the most popular ones, which is widely used in understanding simplest communication systems and gives us simple expressions, and when we try to understand the behavior of a system when it goes through a wireless channel. We would also be interested in the probability density function of alpha squared of t. Now, alpha squared of t is clearly the squared envelope, and squared envelope is going to give us the signal strength directly, and we could write this as p of alpha squared of x is given as 1 by omega p e to the power of minus x divided by omega p, which is equal to 1 by 2 b 0, going by the expression above, e to the power of minus x by 2 b 0, and this kind of expression is the exponential distribution. So, what we can say is that the power of the received signal over a wireless fading channel for the case that we are considering is exponentially distributed. Now, just to remember some of the important things that we have come across while doing these derivations is we made the assumption that phi n is uniformly distributed between 0 to 2 pi. This is one of the important assumptions that we have made. The second important assumption we have made is this n is very large, so that using the CLT, that means the central limit theorem, we can make this Gaussian approximation. So, with that we could arrive at the distribution of the alpha, that is the envelope, which is Rayleigh distribution, and the distribution of the envelope squared, which is giving us an indication of the signal strength, is exponential distribution. So, the signal strength is exponentially distributed at the receiver. Now, just to explain what it means is, suppose we have a transmitter with an antenna, this is the separation distance, and let there be a mobile. In all these expressions, in the last 2 lectures and this lecture, we have never used D. We have never said that the mobile has moved from its location. However, what we have said is there are paths which are reflected, and the reflection could be from a moving surface, or this could be moving, but there is no notable change in the distance within the consideration. Or what we mean is, this mobile is within a region where the average received signal strength is remaining the same, because we have always been talking about tau delta T n in the order of 1 nanosecond. We have taken those examples, and it is almost practically static mobile condition. So, the average received signal strength has remained the same, and in all cases what we have explained is that h of t, which represents the channel strength, or r of t for s tilde t equals to 1, that means for the case where s of t is equal to cos 2 pi f c t, is a function of time, okay. And we have also discussed the case where it is flat across the frequency. So, when we studied the different kinds of channels, we said in small scale fading there is time selective, there is frequency selective, there is space selective. So, at least we have seen 2 things and partially defined one of them. The first thing that we could note is these channel values are fluctuating with time. That means, here the signal is not constant. What we have sent is s tilde t is equal to 1. What we have received is corresponding to that r tilde t, which we have defined as h t in this case. For the case s tilde t equals to 1, is a random variable. For the case where there are large number of paths coming from all directions, and where the mean received signal strength, mean received signal is 0, what we found is this is not only a random variable, it is Gaussian random variable, and it is a 0 mean complex Gaussian random variable, usually represented as ZMCGRV, 0 mean complex Gaussian random variable. So, even though a constant signal was sent, what we have started receiving. So, even though a constant signal was sent from this point, what we kept on receiving is time fluctuations of the received signal strength, and the received signals envelope fluctuates as Rayleigh distributed, as given by this distribution, and the received signal strength is distributed following exponential distribution, and the signal itself is complex Gaussian distributed. So, I repeat that even though we have sent a signal with constant amplitude, what we receive is signal with time varying amplitude, it is a function of time, and the amplitude's distribution is random. Now, this is a very significant observation that we could make in our progress of wireless fading channels, and this time domain variation is resulting in the fade in time direction. In the frequency direction, it is frequency flat and not frequency selective. So, what we keep in mind with respect to this figure is, we have not generated the expression where received signal strength changes with distance. That is already over in the discussion where we talked about large scale propagation model. In this particular model, we are at a location D. Now, this location could be anywhere, either close to the base station or far away from the base station. At that location, there is fluctuation of received signal strength. At that location, there is continuous fluctuation of received signal strength. So, moving ahead further, what we have discussed is the Rayleigh distribution. Now, instead of Rayleigh distribution, in practical scenarios there could be other distributions also, and one of the other important distributions is the Riccian distribution. Riccian distribution is present when there is line of sight component. So, what we mean by a line of sight component is or a specular component, that means between the transmitter and the receiver there is either a line of sight or there is a very strong reflector and one of the paths stand out distinctly compared to other reflected paths. So, its signal strength is much stronger. So, definitely if there is line of sight, usually this is one of the strongest path. If there is a strong reflector, that could also be strong. So, compared to other paths, when one such typical path is present, what we get rise to is Riccian fading, which we are going to describe. So, in that case we have H I and H Q that we have seen is Gaussian random process, but with a non-zero mean as written over here, with means M I corresponding to the real part of the signal and Q corresponding to the imaginary part of the signal. We will also make the assumption that H I and H Q are uncorrelated. The details of such things we will see in the following lecture. In such a case, P of alpha defined earlier is given as x by B0. B0 has also been defined, exponent of e to the power of minus x squared plus s squared divided by 2 B0, and I0 of xs by B0 for x greater than 0, where s is defined as the sum, s squared is the square of the mean of the I component and that of the Q component, and I0 which is present in this expression is the modified Bessel function of the first kind. In this expression, the rise factor k is defined as s squared by B0. So, this is the s squared corresponding to the rise factor, and B2 B0 is the denominator term. When k equals to 0, that means when this k is equal to 0, s is equal to 0. So, you will find this expression becoming the same as the Rayleigh distribution. This is going to 0, this will be I0 of 0. So, hence this will be x by B0 e to the power of minus x squared by 2 B0, which is the Rayleigh distribution. For k equals to infinity, there will be no fading, because this will be a very strong component and which will overshadow all the other components. So, for the rise factor k equals to s by 2 B0 we have defined, and the average envelope power, which is expected value of alpha squared, is equal to omega p, which we have defined earlier, is s squared plus 2 B0, where 2 B0 is the power due to the non-Riccian part, that means all other parts, and this is the power due to the Riccian part. So, therefore, s squared is equal to k times omega p divided by k plus 1, and 2 B0 is omega by k plus 1. Now, if you add these two up, if you add these two components, this plus this, what you are going to get is omega p k by k plus 1 plus 1 by k plus 1, which is equal to nothing but omega p, and which is described in this equation. So, basically this gives the ratio of the power of the Riccian component compared to the total envelope power, and this gives the fraction of power from the non-Riccian component with respect to the total power. Using these expressions, you could expand the earlier expression shown in the previous slide, which looks a bit cumbersome, but it's straightforward. If we replace, we had e to the power of x squared minus of x squared plus s squared by omega p, and I0 of x times s. So, s can be expressed from this and B0 can be expressed from this. So, if you replace these expressions into the previous one, you are going to end up with this. And the squared envelope has a distribution as described by this particular expression. It is a bit cumbersome. Because these are a bit cumbersome, these are not very popular and not very used for an early insight into the system, whereas you have seen for Rayleigh this becomes exponential and this becomes also quite easy to handle. We get very good results. So, an early insight is easily attained through Rayleigh distribution, whereas for this we often need to do numerical techniques or even simulations. Usually numerical techniques work out with these. It is a little bit more cumbersome than with the Rayleigh distribution. It is a non-central chi-square distribution with 2 degrees of freedom. If we look at the distribution of the envelope for Rayleigh case, what we will find is on the x axis is the PDF, y axis is the PDF, x axis are the values for different values of k. Again, this picture is taken from Gordon Stuber. So, I am just reusing the figure for sake of for easy explanation. As we see for k equals to 0, there is this particular curve which represents the one which is similar to a Rayleigh distribution, and as you keep on increasing the value of k, this becomes sharper and sharper and the spread decreases, and slowly as k tends to infinity, there is almost an impulse with hardly any fluctuation in the value of a. This becomes narrower and narrower. So, as has been explained in the previous slide. So, with this what we can see is that the amplitude coefficients which are received are random, although you are sending a constant amplitude signal, a continuous wave transmission, and the signal is complex Gaussian distributed. The envelope is Rayleigh distributed when there is equal distribution of power from all directions. We will see more details, and when there is a specular component, it is instead of Rayleigh distribution, there is Rayleigh distribution. For Rayleigh distribution, the squared envelope, which indicates the signal power, is exponential distributed, whereas for Rayleigh case it is more cumbersome. For Rayleigh case, if you put k equals to 0, you end up in a Rayleigh distribution, and if you put k equals to infinity, that means very strong line of sight. Just imagine a satellite link with hardly small portions from multiple paths. You are going to get almost no fading, and that would remind you that we will be almost getting a AWGN condition. So, if you set Rayleigh factor to be very high tending towards infinity, you almost have no fading situation. So, all the results that has been used for AWGN could almost be approximately applied in those cases. And for the case where k equals to 0, it is one of the difficult situations. So, analyzing for k equals to 0 gives us a worst case analysis of a system, as well as the results are insightful. We can conclude things easily and quickly with Rayleigh, although it is not applicable to every situation, but it does apply in many situations. We will continue with this discussion in the next lecture, where we will talk about the Nakagami M distribution, and followed by we will look into the signal correlation properties. Thank you.